Hello and welcome to this session. This is the purpose-built databases for modern applications. My name is Robert McCauley and I'm a solutions architect here at AWS, specializing in NoSQL and Dynamodb. And I've been a database developer my whole life, so I love talking about databases. What we're going to talk about for the next 30 minutes is these things here. What is a modern application as compared to traditional apps? Why you would consider a purpose-built database for your next application or for a migration? And what are the different databases within the AWS database family to choose from? So thinking about applications, they've really changed, haven't they, over the years and decades. Modern applications now have very different requirements. If you and I were to sit down and think of a new app, maybe a distance learning app or some sort of social media app, how would we scale it? How would we design it for the users? How would we even know how many users to expect? You can see that some of the requirements there. Latency is a key thing. We want to make sure that the application scales and performs well and has low latency, regardless of the users. The request rate, millions per second. What if our application is a smart home device, for example, and it has lots of different devices sending in data every second? These are different than traditional client-server apps, aren't they? Let me tell you a little story about what happened at Amazon.com back in 2004. There was a big crunch at holiday shopping time, and our traditional relational databases were having trouble scaling up to meet the load. There was a few different sources of this problem. The number one thing that I hear is that DBAs and administrators are really overwhelmed and burdened by trying to keep up with the idea of scaling a relational database, keeping the high availability and disaster recovery working. You know, all the clustering, mirroring, sharding, failovers, and what happens when something fails and cascades and other things start failing. That got to be a real problem. So when they looked back at this event and tried to optimize it, they realized a few interesting things looking at the access patterns. Number one was that over half of the requests to the database system were simple key value lookups. Provide a key, maybe a customer ID or a product ID, and get some data back. So they thought, that's simple. It's maybe simpler than we need for a full-blown relational database. The other thing that they noticed was that the joins were incredibly computationally expensive. If you have 2 or 3 or 4 tables with millions of items in them, millions of records, and you try to do a join, at that scale, the database would probably do a hash join, which would put a lot of load on the CPU. So we found the CPU was a real bottleneck here. The engineers decided to take a different approach to designing the tables themselves, denormalizing data so that the data is all there in a single record and a join was not needed. And you might see the same kinds of things as your application takes off and becomes popular. Suddenly you might find yourself beyond the scale of a single server or a single relational database. And jumping from one relational database to many is a big hockey stick in complexity. So there's a new set of way of thinking about databases with serverless databases and managed databases in the cloud that relieve you from a lot of that worry and complexity about what happens when things scale. The other thing we want to do now in this day and age is to provide developer-friendly databases. So things like APIs that are true APIs with GET and POST, as opposed to requiring custom drivers and proprietary middleware and so forth. And we'd like to pay as we go, right? We in the cloud we want to pay for what we consume and not pay when it's not being used. So to accomplish this, I really want you to think about building with purpose and using the right tool for the job. You might be using a single database that you've learned over the years and you're used to, but that might be more of a Swiss Army knife. It does a lot of things pretty well, but it's really not optimized to do a certain job as well as a purpose-built database could be. It also might be overburdened. You might have 10 different customer applications all running on it, all competing for the same limited resources. So the idea of having microservices now and having splitting your application into components and having the best database underneath those components, I think will really bring a lot of value to you. Let's take a look at another case here from Amazon. Prime Day 2019 was a 48-hour event. And during this time, the amount of data that went to our servers, our infrastructure, was staggering. For example, Dynamodb, which powers much of Amazon.com, had 7.1 trillion calls, right? And it peaked out at 45 million calls per second. We also have a huge cluster of almost 2,000 Aurora servers, and they handled 148 billion transactions during this time. That's what I would call an internet scale application. So take the lessons that we've learned to try to architect databases, and we're going to share our best practices with you, and hopefully you'll be well informed to understand what the databases do well, what their superpowers are, and how you might pick a database for your next application. So think about them along these three axes as well. The scale, what is the scale of your application? Do we know how many users are going to be there? Do we know what the access patterns are? Are we prepared for spikes in popularity? Are we prepared for nights and weekends when we want to turn the thing off? Is it going to perform well? How well does it need to perform? Do we need to have single-digit millisecond latency? Do we need to have fully consistent reads, for example? And availability. Is it okay to have this database off for a couple of hours a month while we perform backups, or does it need to be available all the time for our worldwide customers? And throughout this talk, I'm going to be sharing with you some customer examples. Here's a cool one, Duolingo. You might be learning a foreign language now in your free time on your phone. And Duolingo, like many other AWS customers, has chosen to split their application up and use the REST database for the job. As you can see, their primary database is Amazon Dynamodb, and this is what really powers the vocabulary, the words, the quizzes that they use, that you interact with on your phone. They also use in-memory caching with Elasticache, and that's for even faster access than DynamoDB for keywords and phrases, and Amazon Aurora, which is a purpose-built but relational database that can power traditional business transactions and workflows. All right, here we go. Here's a look at the family of databases. And we categorize them, as you can see here, the relational ones that we know and are familiar with. And then the next three are the key value, document, and wide column databases. This is what I'd call the NoSQL or NoSQL family of databases. Slightly different characteristics, right? No more rigid schema, often a key value lookup or key value with sorted sets of results coming back. We're going to go through those. Next, we'll look at in-memory databases. The idea of having a cache or a memory layer to really provide incredible speed and performance, and perhaps to provide a shield against your traditional database for heavy read workloads. And then we'll close out with the three newer ones, the graph, time series, and ledger databases. These are a little bit different maybe than what you're used to, but very well suited for the types of unique requirements that customers have. All right, let's dive into relational data itself. And as we see here, we have a schema with a bunch of tables, right? Traditional apps might have 100 tables easily. And these model entities, they map attributes of different entities that we have, like in the medical situation here, we have patients, doctors, hospitals, visits, and those little linkages, those bars are foreign key relationships, right? And this is the idea of normalizing your data. And it really became popular in the 70s and 80s when disk was incredibly cheap. Disk was the bottleneck, and we really didn't want to store duplicates of data in any way, sense, or form. So we put everything into a separate table and just provided references to it. Everything's highly structured. The database schema is known in advance, and it's difficult to change. Developers typically have to ask administrator to make a change, and that's a big process, right? So it's well if you know your requirements. It's well for traditional apps. It's up and running. It works. Most of our apps today, I think, are still running on relational. So it's got a lot of proven qualities, but it also has some limits, as you heard me allude to earlier. For relational databases, we have the RDS family of database services, as you see. So we can choose from traditional vendor databases or a few different open source databases like MySQL and PostgreSQL, or Amazon Aurora itself, which is our own purpose-built relational database for the cloud. All of these are the same characteristics. They're fully managed. And what that means is it's much, much easier to set up a database in RDS than it would be to not just deploy it on your own hardware, but even easier than to deploy it on your own EC2 instance in the cloud. Right? With RDS, you don't have to worry about backups. You don't have to worry about patching. You can easily leverage the security of the AWS cloud, the IAM policies, and Cognito authentication services. And they're very highly available. Your data is always replicated multiple places across availability zones. And I really like this because this addresses much of the need for doing things like mirroring and clustering and replicating to different areas, right? If you know that your data is always replicated 3 ways, then there's less of a worry about an instance crashing and your data being lost. So the RDS service is there. And there's a lot of innovation and engineering going into all of our databases. Here's what has been released recently for the RDS data databases, and it's a data API, right? So for all those databases, if you've tried and used them in your career, you know that they're all very unique, and accessing them, you have to get special client drivers, you have to configure them, you have to know the ports that they talk on. You probably have to set up authentication and users and groups within the database engine itself in order to support the users. The RDS Data API really addresses all that. It's a little middle layer that acts like a proxy, if you will, and it provides the database services in a real API form, like a RESTful API. So your developers will like this. They can, instead of calling the database directly, they can just make an API call to read and write data. And the connections will be pooled to a degree within this service, which will help you scale up during peak loads. There's even a query editor in the console, so if you need to do simple queries or administrative SQL, you can do that right within the AWS console. So Amazon Aurora itself, this is the engineered database that was created a few years ago, and it's still the most popular and fastest growing database service that we offer. How does it work? It's a relational database that you can run MySQL or PostgreSQL applications against because it's compatible with those APIs. Internally, what we've done to support the performance and scalability is we really split apart the storage and the compute services of the database. So the compute nodes you see on the top there, and they are split across 3 availability zones. The storage itself is managed separately, right? And the storage really relies on the log of the database. No longer does each instance, each running instance, acting as a monolith, have to write data to its pages or manage the pages or do checksums and things like that. Instead, it simply just writes to the log like it always does, and then the shared storage volume will take those logs and apply them to the database and keep it up to date. So that right there results in a huge reduction of I/O and a performance boost versus a traditional MySQL or PostgreSQL database. Expedia, the travel company, they use AWS databases. They're using Amazon Aurora right now for operational queries. They're using Amazon Elasticache for stream processing. And you can think of Elasticache as a cache or as a kind of a database, if you will. They also use Amazon Redshift. We haven't included Redshift in today's talk. It is a database, of course, but it's really in the analytics family within AWS, so you might find content on that in a different talk. All right, moving on from relational to key value data. This is what really gets me excited. The key value data is what developers love, right? The idea of having a JSON document or an XML document in years past, I suppose. But the impedance mismatch of trying to take your data in JSON format in your application and format it into an SQL query with rows and columns, that's tricky, isn't it? Right, what if we could just put the whole thing into the database? Tomorrow we want to get it back out by a key, we just request it by that key and it all comes back in, and now our application has the full state of whatever we are tracking. Very, very popular way to store data. So the NoSQL family, they all have key value characteristics, as we'll see. They're all similar, but they have a few unique characteristics, as I'll talk about. The first is Amazon DynamoDB. And this is our original NoSQL database. This was created, the idea was sparked in 2007 when our CTO, Dr. Werner Vogels, and others created an academic paper called DynamoDB. And they really explored this idea of a key value lookup as a specialized type of database that was different than the relational databases of the time. Amazon DynamoDB itself was released in 2012. And it's been running almost everything within Amazon, within AWS, across Alexa, where I used to work. All of our engineering teams, would choose DynamoDB as the default service for any new applications. So it's really proven. It's battle tested. It's operational. It's been through the ringer. It's a very solid database. And over the last couple of years, it's gotten a lot of enterprise features as well. So the idea of the security, everything's encrypted at rest and in transit. encrypted at rest with our key or your key using the KMS service. We now can very easily do global replication, where we can set up a copy of our table in a different continent and have the system automatically populate that data and keep it up to date with under 1 second latency typically. Dynamodb itself is a very serverless environment, so there's really just an API that your developers will call reads and writes to. The billing can work in the same way. There's a couple of billing modes. But here we see the provisioned capacity, the reads and writes that you might ask Dynamo to handle. And you can see that we have a feature called auto-scaling. So in the orange line here is our traffic. Maybe it dips down at night and comes back in the morning. So what auto-scaling will do is automatically look at the traffic itself through CloudWatch and apply changes to your provisioned capacity, either crank it up or bring it back down according to parameters that you set. Maybe you want to have, in this case, looks like about 20 or 30% headroom, just in case. So that's fine. If you have a really sudden spike, it looks like it's able to handle it here. So auto-scaling is just one of the many features. We also have on-demand, a pure pay-as-you-go pricing model. Netflix, I'm sure you've been watching more movies these days like I have. So Netflix uses DynamoDB for their preferences really across a lot of their service. And it really works well because it's easily worldwide with global tables, and it provides that nice developer-friendly interface. All right, moving on a little bit, there's another category of databases which I'll call document databases. And these are taking that idea of the JSON object itself and really exposing more and more functionality. Here we see a JSON, some code that might aggregate or do a search within a document. And that's really important, to be able to provide those indexes and functionality to look in documents and find the one that you want, where it might be nestled and buried deep within a document. Of course, the documents themselves are very flexible. There's no real constraints on the structure of the document. So if you wanted to suddenly start storing a picture of your cat, that's perfectly fine, and you can do that with document databases. So Amazon Documentdb is a relatively new service that we have, and it's a document database that's designed to be MongoDB compatible. So if you're a developer using MongoDB today, take a look at this, because you could probably port your application over to Documentdb without any issues. It came out last year in 2019, and it has a ton of features available. So some of the features you'll find in Documentdb are, there's over 40 features that it released with 40 APIs. There's database auditing, there's slow query logging, there's the idea of change streams. And this year we also have more engine updates. We have functions for expressing data, formatting data. We also have role-based access control now. And just recently we released cross-region snapshots. So all these should help you adopt a document database. If you look internally, the architecture and the behavior of Documentdb for administrators, it's really similar to Aurora. So you'd choose the instances you want, the size, and you'd have an endpoint with which you can access the database service. All right, next is a wide column store. Wide column is a term that really just means flexible schema, right? You have a key and you can have different types of columns. And Apache Cassandra is probably the most popular type of wide column database out there. It's a NoSQL database. It uses the Cassandra query language. And what they've done here is, they've provided a query language almost like SQL on top of the database. DynamoDB and Documentdb have more of a pure API. So if your developers are asking, like they ask me often, where is that SQL interface? If they want to have that kind of interface, then take a look at Apache Cassandra, or as you'll see in a moment, our offering for Amazon Key Spaces for Apache Cassandra. It's a managed service offering. It's a NoSQL database that we have that really is Apache Cassandra compatible. So Amazon Key Spaces for Apache Cassandra uses the CQL API version 3. There is a CQL editor right in the console, which is nice, or you can use the CQL SH command line client that you might be used to. Very scalable. It provides 3,000 CQL queries per second per TCP connection. And it provides some unique functions like range delete that you probably wouldn't find in other NoSQL databases. The key spaces is a concept within Cassandra, like creating a database itself, and we can create column families. So all the things that your developers are maybe used to with Cassandra, you can leverage those with Amazon key spaces right now. And this database shares a lot of the DNA with Dynamodb itself. So it's a little bit more serverless. It's essentially you provide the provisioned capacity settings that you want, the number of reads and writes, or on on-demand mode where you just pay per request. All right, let's move ahead to in-memory databases. What are the things that customers are telling us they want from an in-memory database? I think the first thing that comes to mind is caching. You might have heard, of the need for caching. If your website becomes really popular suddenly and your relational database is getting like 100 reads per second, that might be too much, right? So if the data is not changing, if it's fairly static, if it's just a product catalog, for example, then go ahead and put a caching layer in front. But in-memory databases can be so much more. You can use them for analytics. You can query the data that's in there. You can, oftentimes you'll see them as leaderboards. You finished a game and you want to see how you rank suddenly with everybody else in the world. It could be a way to cache, media assets, video clips or audio clips that are going to be popular and be requested. Also could be a great session store, as we'll see. The service that we have within AWS is called Amazon Elasticache. And what this is we're taking open source engines like Redis and Memcached and providing them as a service within the cloud. These are fully managed. They're set up in an environment where you'd have recommended at least 3 or more nodes in a cluster. So the big worry that people have about an in-memory databases is what if you kick the plug accidentally and the whole thing dies and the memory is suddenly lost? It's unlikely to happen because if you set it up with a 3 or more node cluster, then you have the high availability. If a single node dies, you can have it rebuild itself automatically, and the other 2 nodes will handle the load and keep everything consistent and up to date. Using Elasticache as a session store could work like this. You build your application, you have a load balancer, you have a fleet of web servers out there that are handling the traffic. But do we set up sticky sessions? Do we want to make sure that when the user comes back 10 seconds later to click on page 2, they come back to the exact same web server? That concept of sticky sessions has been somewhat popular, right? And that'll ensure that whatever state they were in, whatever cookies or things state you want to remember is on the web server. That works well, except that web servers crash sometimes, don't they? Right? So the idea of having a session that's independent of your web server fleet is very powerful. And you can do that with Elasticache. You could essentially design your application with a session ID and look that up every single time somebody clicks or makes an action on their phone. Use that session ID to hit Elasticache. Within a millisecond or so, you're going to get the answer back and the state of whatever workflow they were in, and then you'll be on your way regardless of the state of the fleet of web servers. And we talked about leaderboards, but the Peloton, the at-home cycling company, they're using this. If you finish your workout tonight and you want to see how you rank and you want to take a look at the leaderboard, you probably won't have to wait too long to see what your ranking is. So it's using Elasticache to get that near instant performance and to rank you and show you how you're doing. All right, moving on, the last 3, the new kids on the block, the cool databases, if you will. The first we'll talk about is the idea of a graph database. Not to be confused with Tableau charts and pretty graphs. This is more like a conceptual graph. Things like social networking connections, recommendations across products, knowledge graphs. If your voice assistant like Alexa, if it talks about a topic, she might compare it with an encyclopedia of related topics to guide the conversation. Also very useful in fraud detection. If you're getting hit by fraudsters, and their address changes, but maybe their phone number doesn't change, or maybe their last name is the same as somebody we know is fraudulent from a similar address. All those sort of connections, they're a little bit vague, but they're hard to map and do well, unless you have a purpose-built graph database, right? So here's another look, just combining the idea of a social network with a product recommendation engine. So we have connections between people. We know certain people like certain products. We know some people know other people. So we could use a graph database to run a query to make recommendations. Hey, did you know that other people that you like or similar to like this certain product? Check it out. or even just purely social. You know, Bob and Alice don't know each other yet, but they have friends in common. Maybe they should link with each other. If you try to build a graph solution using a relational database, it's possible, I suppose, but it's going to be very difficult. You're back to the idea of creating multiple tables, creating foreign key relationships, and then doing those really difficult joins. It's difficult for the database to join all these things together and provide answers. I've seen this done before in the past. I've certainly, as a relational guy, I've seen people do all kinds of crazy things with relational. But the real challenge here, not just is it complex and would require like a 5-way join, but you really don't have the chance to do fine-grained relationships. And what I mean by that is the links between people are either all 100% or none. In a true graph solution, it would be nice to say, hey, this connection is only 10% strong. You know, these two people know each other, but they really haven't interacted in over a year. So maybe we'll make that a weaker connection. And now the service itself is much more powerful to use that data versus all or nothing connection. So the service we have is called Amazon Neptune. It's a purpose-built graph database for the cloud. So you can check it out. It's a relatively new service, but it's leveraging open source technologies and languages that you might be used to if you've built graph database applications in the past. So we support open source Apache Tinkerpop and W3C RDF graph models. And your developers will be using languages like Gremlin and SparkQL. You can find some pretty cool demos and build it yourself tutorials online for Neptune. My favorite one is the Kevin Bacon Degrees of Separation app, where you plug in an actor or actress, and it finds what's the fewest number of movies that they might have had in common with another common actor until you get to Kevin Bacon. It's usually a pretty low number. All right, moving on. Next is the idea of a time series use case. And this is a little bit more graph, I suppose. You see a chart there. I've come from a manufacturing and industrial background working at Amazon Robotics. And we did time series uses all the time. We would have to measure the things in the factory. We would measure the quality of each of the products we were creating. We would want to be notified if anything dropped out of range. We'd want to be notified if the moving average is going up and down. There's all sorts of triggers that you want to look at across a time series and be able to query easily and effectively. Characteristics, as you see here, very high volume. It could be, a million IoT devices across an industrial setting or an agriculture setting that's pounding your database with inserts. You might want to be able to query that immediately, or maybe you want to do a longer query the next day where you do some sort of roll-up of 10 million records. You also want to be able to delete that easily. A month later, maybe that terabyte of data is not useful anymore, so you want to be able to quickly drop it and saves the cost of storage. We have Amazon Timestream, a fast, scalable, and fully managed time series database. With Timestream, we have two storage tiers. There's a very fast in-memory tier for collecting data at huge volumes. And then there's also a configurable movement to a lower cost disk-based storage tier where you do your analytics. The analytics functions we provide are really rich and help you answer business questions. For example, you can smooth your data, interpolate your data, fill in missing data, the types of things that's really hard to do with a relational database. We automate rollup and compression, and it's a fully serverless, so you can just call it through APIs. You don't have to worry about setting up instances and servers and the size of your fleet or anything like that. All right, the final one is the idea of immutable and verifiable data. I won't give it away just yet. But the customers tell us, some customers who are in very leveraged, very regulated environments like finance, healthcare, government, military, they really want a database that's impossible to meddle with. There's always an administrator or two, isn't there, that's got super user access. And they could, if they wanted to, if they were inclined, go in and change past data. And that makes it very hard to audit the data. It makes it hard for regulators to have confidence that the data has never been changed and never been touched, and it's trustable. So the Amazon Quantum Ledger Database, or Qldb, is our offering here. It's a new database that's a managed ledger database. So it's write-only. You just write to it, and it uses cryptographic functions to ensure that the writes are recorded, and we know who recorded them, and we know that nobody else has changed them since that time. BMW is building this digital vehicle passport app. And the way it works is it applies those use cases to a used car. So if your car has a history. If it's been an accident or if it's had its maintenance done or not done on time, you would be able to use Quantum Ledger database queries within this app to figure out what the history of the car is and see that very clearly. All right, so we've given you a very quick whirlwind tour of the database family. Invite you to check them out. Know that we're continuously innovating. We're building features according to what our customers, request and what you tell us is important. Please find out more information at the link here, aws.amazon.com/databases. You can contact us. You can contact me, Rob McCauley, anytime. I'd love to hear what you're building and what your questions are. There's also some new material here. There's a classroom training and there's a certification for certified database specialty now. Thank you for your attention and enjoy the rest of the summit.